Hey everyone, wanted to make a lecture video to keep us on track with the snow day and everything like that. So having said that, uh, essentially this module is all about computing. And computing, one of the things to understand about it is an emerging technology known as containers. So let me give you a sort of overview of what a container is. A container is something that holds something. That's what it is in English. Now, in technology, what a container refers to is going to be a package that contains, or that holds rather, so we're not using the same word, it holds every single thing needed to run an application. Now, that is going to include the application. That's going to include the operating system. That is going to include the various components, be they libraries. It's going to include any sort of dependencies. All of that is all held inside of a container. Now that's going to help us a whole lot with security. Because a lot of times what we see older applications that we still want to use as an enterprise. Application licenses are expensive. Sometimes those applications that have older, that are maybe a little bit older, they're not the most recent version, that's reality. We still want to be able to run them safely. But they might need older version. A very common thing is like an old version of .NET, an old version of Java. And look, any way you slice it, those old versions often are riddled with vulnerabilities. Those vulnerabilities, like I mentioned in an earlier lecture, more than 52% of successful attacks on IT systems, over 52%, use vulnerabilities that have been patched, not just known about, but patched for 2 or more years. So one of the benefits of a container is that you can put those old dependencies, be they an old version of Java, old version of .NET, old version of Silverlight, old version of Flash Player, whatever the dependency is. You can put that into the container and only allow it to be run with your application, not allow anything else to use it. That's going to greatly reduce the likelihood of one of those vulnerabilities being able to be exploited. It also basically takes your infrastructure and it standardizes it so that every customer is using essentially the same exact setup. There's no difference there. That's going to be vital. That right there greatly reduces the support cost. Because then you as a company, if you were providing a containerized application, the container, one of the big benefits of them, if it runs one place, it'll run another. What that translates to for you is the fact that that container is just going to be able to run and run flawlessly every time. So, think about it for a second. If we were in the class, I would ask this question. I would say, hey, how many of you have the exact same computer? And a couple of you might have this. If you all started around the same time, maybe a lot of you bought the same base configuration MacBook Pro or the base configuration MacBook Air, something like that. But then you dive a little bit deeper. How many of you have the exact same version of the operating system down to the updates? It's possible 1 or 2 of you might, but then you ask another question. How many of you have the exact same applications installed, the exact same versions of those applications? And you start to see that there are millions and millions of hardware and software combinations. It's very rare to see 2 devices that aren't managed by a central authority like a company or like a school have the exact same versions of stuff. Here's the thing though, different versions of different applications and different software versions, that can make a huge difference in how things run. I'm sure in your 4600 class you experienced the problem, a local Java application running fine on your computer, not running on maybe your buddy's computer or your instructor's computer. That doesn't happen with containers. If a container runs one place, it will run any place capable of running a container. That's huge. That's a huge benefit. I cannot possibly overstress that. They reduce cost. They're cheaper to run, they're cheaper to manage, they're cheaper to support. And lastly, they can handle legacy applications very, very well. One thing you might run into, especially if you go into a more IT-focused career and a less like development or a less consultant, just go into a more IT career, you'll run into this. You have legacy applications you have to support. It's a whole lot easier to just plop a container that you know will run than to sit there and try to find an old version of like Windows 95 or Mac OS System 8 or something like that that's just way old and way hard to find. The containers simplify that. So they're a huge benefit. Now, we're going to talk a lot more in depth about containers because if you don't know, the final module of this class, which we'll spend about 2 weeks on, is all about containers. So I'm just going to give you the high points for today. And that is Docker. Docker is a great platform to make containers on and also to run containers on. Now, here's the thing. Like a lot of enterprise software, it contains a community and an enterprise edition. The difference there is not the features. They do the same thing. They both function the same way. The difference is actually the support. So essentially, if you are an enterprise, you want to have enterprise support. You want to be able to pick up the phone, call someone, have, instead of a service level agreement, a dedicated amount of time. Maybe if you report an issue, they have to give you a solution within 8 hours or 4 hours or whatever the time is that you specify in that agreement. That's what an enterprise support agreement is. Now look, if you're a hobbyist and you're using Docker to build containers just to maybe have Home Assistant or whatever sort of program you want to have it run, maybe you have a home lab set up or something like that, and something breaks, it's not going to lose you money. It might lose you a couple hairs, it might lose you your natural hair color, but it's not going to lose you money. In contrast, if you're an enterprise, every bit of downtime, every single bit, costs revenue. It has opportunity cost. Some of that opportunity cost you may never get back. Particularly in an industry with a lot of competition. That's one of the things we talk about when we talk about pent-up demand. We talk about the idea that demand, just because it's once there for your business, doesn't mean that it will be there in the future if you can't meet it. Sometimes it will, sometimes it won't. It depends on the customer's alternatives and if the customer can wait. To understand that, I often use an example of a craving for fast food. Now, I'm a big Taco Bell fan. Maybe you like McDonald's, maybe you like Chick-fil-A, maybe you like Arby's. I don't know. But pick your favorite fast food. Let's say you're really craving an item from there. And you realize, you know what? They're closed. Do you go hungry? Or do you not find a substitute good? Do you not find a substitute food? Do you not find somewhere else to eat if your favorite restaurant is closed? I would venture a bet that you probably don't just say, well, you know what? They're closed. I'm going to go on a hunger strike until they reopen. I would venture to bet that what you do instead is you say, well, let's figure out where else I can go. Because it's not an acceptable solution to just go without food. That makes no sense at all. It is not logical to just skip eating. So we don't want to do that as a business. We want to understand that we don't always have the benefit of pent-up demand. We cannot assume that our customers will come back if we cannot fulfill their demand. So if we have a problem with our containers, or if we have a problem with Docker itself, we want to be able to get support for that. That is why we get the enterprise edition of stuff. Now, I told you I'm going to go into more detail about this container architecture a little bit later in the semester. But for now, what I want to do is just kind of talk about what it has. And you can see that the Docker engine contains all these different components, and it contains the application itself inside of the container, But then look at the bottom, it contains the whole operating system. That's crazy. But when you think about it, it's actually not as crazy as it might sound. Because what's going on there is the Linux operating system, it's not to be confused with like a full desktop version of Linux that you might use. Maybe Ubuntu, or maybe, Linux Mint, or all these different distributions of Linux. It's a very stripped down operating system. It has everything needed and no thing that's not needed. So it only has the basics. And you can often get Linux to fit on about 50 megabytes of space. Yeah, that's 50 megabytes. Okay? I'm not going to have any graphical components on 50 megabytes, although there are some Linux distributions that are smaller than 50 megabytes that have graphical components. But what we're talking about here is just a stripped down Linux distribution. Very stripped down. So yeah, overall the container is going to be a little bit larger than just an application because it contains the operating system, because it contains the application, and because it contains all the dependencies. But the actual difference, when you really boil the math down, is not that significant. So, another concept that we want to understand is serverless computing. When you hear the term serverless computing, you probably think about computing without servers. That makes perfect sense. The name is serverless computing. Whenever you have the less suffix in front of or behind a word rather, it means without that thing. So you see serverless, you think without servers. But that's not really what serverless computing is, even though it would make sense if it were. Instead, serverless computing is a different way of doing computing where you're not reliant upon having a lot of servers that are constantly waiting to receive things to do. Instead, this is event-driven computing. What happens is not the fact that you have these servers that are just doing nothing, waiting for... They are essentially event-driven. So they're going to be executing something whenever the event is met. And that event is going to be some sort of a trigger condition. There's all sorts of trigger conditions that could be used. Maybe it's you receive an email. Maybe it is a form is submitted. Maybe it is you receive an order. Okay, a lot of times we see these in various Home Assistant platforms and various AI platforms as well. Particularly some of the traditional sort of platforms we've seen, like Amazon Alexa. Okay, Amazon Alexa works with a platform known as Lambda. Lambda is going to be the sort of AWS serverless computing. So it's not constantly running, it is execution based. So it is only running whenever the condition is met. But there still has to be a server listening out for that condition, so don't get confused and think that this means computing without servers, because it does not. There are still servers involved. Now, serverless computing doesn't have to have physical servers either. Okay, a server is not so much a device as it is a task. In other words, you could have a desktop computer do server task, and therefore it is a server. It can also be a desktop computer. Now, a lot of times you have a traditional client-server architecture where you have a dedicated server doing a dedicated task, like a print server that manages print jobs. Or maybe you have a dedicated application server that hosts an application that different devices can access. Or a file server where files are shared and stored. Those are pretty common servers to have. But you don't have to be limited to the client-server architecture with serverless computing. You could use peer-to-peer, where there is no dedicated server. Every device functions as a server. So that's pretty common. We've seen that in a lot of online games, particularly games with a lower budget. They don't have to pay for servers. They can host the gaming events. They can host them and matches and stuff. They can host peer-to-peer. So every device shares information, and we also see it with a lot of file sharing, particularly file sharing that's not necessarily known for its legality. So you can also use cloud-hosted servers. There's a multitude of different possibilities for serverless computing. Now, I have a graphic here that outlines some of the evolution of computing. This comes from that Deloitte article that's posted on this module. I don't want you to think about these progressions as being a linear thing that every single company is embracing at the same time. These are trends that are emerging. These are not to be confused with the end-all, be-all, absolute. Every company is doing these things. So we see some trends in hardware there where we used to have very large enterprise data centers. And then we realized, well, the problem with that is that there's a problem with a location. One location, that's a single point of failure. So we moved to a co-location perspective where instead of having a huge enterprise data center, we maybe separated that out somewhat to avoid having that big point of failure. Well, the natural progression from there is to embrace cloud computing. And then after that, we moved to a hybrid cloud model. Okay, so there's all sorts of possibilities that we have for enterprise hardware that don't necessarily involve some big monolithic approach to it. Same thing with the atomic unit of computing. It used to be we had one physical server doing one server task. But we realized very early on that's a very inefficient way of doing things. So we moved to a model where we have fewer physical servers, but the physical servers we have more power. And we use that additional power to host virtual machines. So each virtual machine can be running one server operating system that does one task, but it's not one physical server per physical task. It's one virtual machine per server task. And that's important because you don't just want to throw everything on one server. Because if you do that and you have to update, you're losing a lot of downtime. You're losing a lot of systems. So you want to separate things out as much as you can in technology. That brings us to containers. Containers shrink that down even further. Okay, so we have a lot less stuff that's running, a lot fewer moving parts. And then we separate that out even further by, instead of having servers, we have containers, then we have functions. Okay, and then that brings us to software architecture. We used to have these huge monolithic applications. In 2090, we talk about the enterprise resource planning system. But we can shrink that down and use n-tier. We can shrink that down further. We can do microservices, and then we can do serverless computing. Now, these big consulting firms, I like to identify these big overarching trends. But like I cannot emphasize enough, not every company is embracing every single one of these. It's just these are the progression of technology. This is sort of what's hot right now, not necessarily what is everywhere right now. So this kind of goes on. This is also from the Deloitte article here, talking about some of the different approaches, some of the trends that you're seeing. So some of these I'm going to kind of go through a little bit. You have a trend where you're having the event-driven approach. That is the serverless approach. You're having less ops. You can't get rid of all ops. Okay? It's not no ops. It says that right there. But you're greatly simplifying the ops by essentially taking a lot of the traditional troubleshooting and operations out of software development. You're putting it into containers so that there's a lot less troubleshooting to do. And then paying for execution time. That is cloud computing. That is where you're going through and you are really just embracing the cloud computing. You're paying as you go. You're paying for what you use. You're not investing in stuff you can't take use of. So, Amazon has the EC2 wizard. We're going to be using EC2 a couple times this semester, and I don't want you to be afraid of it. EC2 is a very simple way to set up a virtual server. So essentially, one of the first things you're going to select is the Amazon machine image. Amazon machine image is simply the operating system. So they will basically say, hey, you can use Amazon Linux, you can use OpenSUSE, you can use Ubuntu, you can use Windows Server. I think they even have an a Mac OS server of some sort on there as well. You can pick from all those different machine images. You select that, that's going to go ahead and give you a sort of machine ready to go. You set the instance type. You give it your different amounts of resources, your different tiers of service. You set up the network settings, what's allowed in with the server, what's allowed out of the server. You set up security groups and stuff. You set up the IAM roles. We talked about those last week. You set up the storage options. What's the speed of the storage? What's the capacity of the storage? You apply it tags. You might think, why are tags important? Well, I'll tell you why. Tags are how you find the server later on. Yeah, that's a very important thing to be able to do, to be able to search for the server, to be able to say, this is the server that I want, find it. Because a lot of organizations, they have thousands of different EC2 servers. The tags make it a lot easier to find the server you're looking for. You can assign it to a security group, and lastly, set up a key pair. So we're going to be using VOC key in this class. That's sort of given within the AWS Academy Lab. Just really easy to work with that. Now here's a graphic that goes through this, and it's basically just applying those steps. So you set up, you create the new EC2 instance, then this is for creating the Amazon machine image. So you launch the instance, you capture it after you do all the modification to it, then you have a new Amazon machine image that you can deploy to other EC2 instances. So for this lab, the second lab, what you're going to be doing, or what you already did, I guess, is launching a web server with termination protection enabled. You're going to be monitoring your EC2 instance. You're going to be modifying the security group to make sure that it allows HTTP requests into it. Then you're going to be adjusting the EC2 instance to meet the needs of the organization. You're going to be looking at some of the limitations of EC2. You're going to be testing the termination protection, and then finally, you're going to actually terminate the EC2 instance. Now, terminating the instance is something that's very important to do because you don't have unlimited funds, particularly if you're an organization. You know, I always say to students, be very careful if you decide, hey, I want to make my own AWS account. Because you can do that. You're perfectly free to do it. But a lot of times you end up going beyond what the free tier will do, and you end up with a big bill. And essentially that bill comes from the fact that you didn't terminate the instance. You left it running all the time, which is going to rack up usage. So be very careful with that and make sure you understand how to terminate the instance. So I certainly hope that was helpful. Also, hope you have a great rest of your day. Look forward to seeing all of you back, hopefully the end of the week. So y'all have a great day.